Okay, so yesterday we have discussed about a resistive circuit, okay, alternating current in a resistive circuit. So there we have derived the equation that if V is equal to V sin omega t or V is equal to V max sin omega t, okay, voltage that is called instantaneous voltage, okay. So if instantaneous voltage V is equal to Vm sin omega t, then I is equal to Im sin omega t. Okay, so Im is nothing but equal to Vm by R, right? So there is no phase difference between current and voltage in a resistive circuit. Okay, so uh, current and voltage are in same phase. Okay, so then the next like other than resistors there can be inductors, there can be capacitors, or there can be combination of inductor and capacitor, combination of inductor plus resistor, or combination of capacitor plus resistor, or combination of inductor plus capacitor. Okay, so you can have a LR circuit, you can have RC circuit, you can have LC circuit, you can have LRC circuit. Okay, so we have relationship between voltage and current. We can have some governing equation for voltage and current, and what is the phase angle, how is the relationship between voltage and current. Okay, so there is long derivations involved in that. I will not go into the derivations. I will write down the major formulas after derivation, what is being derived. Okay, after derivation, how we are the final formula that we have arrived at. Okay.
Yeah.
So first we will start with the like a LR circuit. Okay, we have done resistive circuit. Okay, resistive circuit. Okay, so this is alternating current. Okay, so we have resistive circuit. So resistive circuit we have told I is equal to Vm by R sin omega t. Okay, that is I max. I is equal to V by R sin omega t. V, as we showed, that is instantaneous voltage. In AC it is instantaneous. In DC it remains constant always,
Yeah.
but in AC it is a function of time.
Changing every
It is a sinusoidal function of time. Okay, so V is equal to Vm or V max sin omega t. Here. So we were discussing about yesterday we were discussing in our household power supply. We say it is 220 volt. So what is this 220 volt? Is it Vmax? The answer is no. It's not Vmax. It is Vrms, which is the effective voltage. Okay. So the Vmax value will be equal to root 2 into Vrms. Here. So it will be kind of 1.414 into 220 volt. Right. This is your max voltage. Okay.
310.
So yeah, and then we have drawn uh, the time versus voltage and current curve. We have drawn that, and we we had two curves. Okay, so let us say this is my voltage, right, and this is my voltage. Then this is my current. Okay, so this is my current.
They're
So
in phase.
so you can say they are in phase. Okay. So this is resistive circuit that we have solved. Then this is called resistive circuit. Similarly, we will now get into the circuit, which basically this circuit looks like this. like you will have this AC source is represented like this, and then you have a resistor. It looks like this. Okay, so this is resistive circuit. Then we will go to LR circuit. Okay, LR circuit. Okay. So what is the governing equation for a LR circuit? Or let us do first the inductive circuit. Let us do a inductive circuit first. Then we will go to the LR circuit. Okay. Yeah. So let us go for an inductive circuit first. Okay. So we'll go for an inductive circuit first.
Only inductor.
Only inductor will be there in this L circuit. Okay. So how does the L circuit looks like? So this is this. This is inductor is nothing but a coil, right? So this is my R circuit, and this is my L circuit. So what is the governing equation for a L circuit? Okay. So the governing equation for a L circuit is V minus L di by dt is equal to 0. So what is because this is as per Kirchhoff's law, like the total voltage drop, the total voltage in a circuit is equal to 0.
Yeah.
So your supply voltage, let us say it is V, and your inductive voltage, okay, whatever L di by dt. So why this negative sign? Because inductance is a property which opposes the increase in current, right? Inductance is something which opposes. So if inductance increases, it will oppose the rate of change of current. They are opposite to each other.
Yes.
Okay. So that's the, as per Kirchhoff's law, the total voltage drop is equal to 0, and V is equal to V minus L di by dt is this, right? So it is being written by the source connected to inductor. Usually the inductors have appreciable resistance in their windings, but we assume that these inductors are negligible. So this inductor will have, we are assuming that it has negligible resistance. Okay.
Yeah.
Okay. So this is the governing equation. So now then if I that what does that mean? Di by dt is equal to V by L, right?
Yeah.
Di by dt is equal to V by L. So what is this V? This V is equal to V max sin omega t.
Yeah.
My V is equal to V max sin omega t. So this thing I can write as V max sin omega t divided by L, right? So let me try to integrate it, okay? Let me try to integrate it. So what I will do here, di by dt into dt integration is equal to V max sin omega t divided by L into dt integration, right? Clear?
Yes.
So if I integrate it, I know like integration of sin omega t is what? Minus cos omega t by omega, right?
Yeah.
Remember now, there is
Yes.
omega term.
Yes.
Okay. So cos omega t by omega. So if like say my V max by A, max is always constant, L is a property, so V max by L is constant. Okay, then my sin omega t dt, right? Sin omega t dt, right?
Integration.
This is my integration. correct? So if this is my integration, then this becomes V max by L cos omega t by omega minus, right? So finally, if I simplify this equation, this cos omega t is what? We know cos omega t is so I know sine pi by 2 minus omega t. Okay, sine 90 minus theta is equal to cos theta. Okay, is equal to cos omega t, right? So if I put a minus sign here, like so sine omega t minus pi by 2 is equal to cos minus cos omega t, right? So minus cos omega t. So this minus cos omega t I can replace by sin omega t minus pi by 2, right?
Yeah.
So V max by L, okay, then sin omega t minus pi by 2. This is my equation. Finally, this is my equation for current. Okay, what is my final equation? I is equal to V max divided by L into sin omega t minus pi by 2. Okay.
Where did minus go?
The minus because this is minus cos omega t is nothing but sin omega t minus
Oh,
pi
because
by 2.
omega t minus pi by 2, not pi by 2.
Pi not pi by 2, minus sign. Okay. So your first we have written my V is what, like I have written my V is equal to V max sin omega t, right? Correct?
Yes.
V is equal to, so this is my equation 1, let us say this is my equation 2. That means what you are able to interpret from here, okay? Your current is lagging voltage by a angle
Pi by 2.
Okay, so this is, after deriving we have concluded that the current is lagging the voltage by a phase pi by 2. Phase angle pi by 2. Okay, so you can take a picture of this. Yeah. Okay. So here in resistive circuit, you can see that the current and voltage are in same phase, whereas in inductive circuit, the voltage and current are not in same phase. In fact, the voltage is leading the current, okay, by angle pi by 2. So that's the major difference. Like that's why because the power normally we write it as VI cos phi. Okay, so cos phi is the power factor. So if the angle between the voltage and current is 90 degree, cos 90 degree is equal to 0. Cos 90 degree is equal to 0. So a capacitive circuit or inductive circuit, it is called as wattless power because cos 90 is equal to 0. Okay. So let me draw this resistive part and we will draw the diagram like time versus voltage and current. Okay. So for the inductive circuit, how does it look like? The does the, how is it looking like? Let us say this is my time, okay. So my voltage is leading, okay. So this is my, if this is my voltage, okay. So that this is when it is 90, it will be 0, like that, because it is lagging by 90 degrees. So when it is max, it will be 0. When it is 0, it will become max, end up, okay. So and when this is max, okay, so this is something like this, okay. So yeah, when this is max, this is 0. This is my current, voltage is leading. So if voltage is leading, its maximum point will be after pi by 2. So let us say here, let us say this total is, let us say this is my 0, okay. This corresponds to pi by 2. This corresponds to pi, okay. This corresponds to 3 pi by 2. This corresponds to 2 pi, okay. So so this is pi by 2, this is pi, okay. So this is max at this will be maximum at pi, okay. So this is 0 here, so this will be kind of like, say, yeah, okay. So this point, okay, it will be at this point. When it is 0, this is max, right? So this is your max value, and let me draw it properly, okay. So this is your max value, okay. Just try to connect it like this. This is your max value, okay. So this is your max, okay. This is max. Then at pi by 2, when it is max, this will be 0, right? This is your max. Then this is your 0. Okay. So this is your voltage, and your current is lagging. Okay, so this is pi by 2. And when this is 0, this will become max. Okay, when this is 0, this will become negative maximum. And then you will follow this. Okay, so this red one is my voltage, whereas this green one is my current. Okay, this green one is my current, and you can see that when this is maximum, my current is 0. That means when this is my voltage is leading by a phase of pi by 2. Okay, so my current is lagging. Okay, so you can see it from here. When it is 0, it is when it has voltage has already started, it is still by
negative.
It is lagging, and the magnitude of voltage and current will depend on the resistance. If resistance is 1, then it will be exactly same. If resistance is more than 1, then
but in all cases it will lag by pi by 2.
Always, yeah, it will lag.
Just the same thing, but at different values.
Yes. So that is the one. So if we see the corresponding vector diagram, or we call it as the Phasor diagram. So if we see the corresponding phasor diagram, so let me draw it like this. Okay, so let us say this is kind of time versus voltage and current. Okay, so yeah, so if this is my voltage, okay, in the phasor diagram, if this is my voltage, like my current is lagging by pi by 2. So this is my current. Okay. So say this is my voltage and this is my current. Okay. And then this angle can be called as omega t. Right. This angle is omega t. So the component, so this component, so you can consider it as your magnitude. This magnitude of the vector is nothing but your V max, right? So this magnitude of this vector is nothing but your V max. Okay. So if you take the component of that vector, so this is the component of that vector is nothing but V is equal to V max. This is sin omega t, right? That's the equation. That's how we are representing. So on the y-axis, if you project the this vector, which is at an angle omega t, okay. So in your so this is if this is omega, this is omega t. Then if this is omega t, this is also 90 minus omega t, then this is also omega t, right? This angle. Okay, so this is nothing but your I cos omega t, right? This is I cos omega t, that is I max cos omega t, and that is V max sin omega t. So you can see that cos omega t, you can write it as pi by omega t minus pi by 2 or whatever. So there is a phase difference. So that this is cos omega t, or you can write it as I max. This is sin omega t minus pi by 2, right?
Yeah.
Yeah. Sin omega t minus pi by 2. So that's what the component. So the instantaneous voltage is actually this projection. See, whatever we are showing it is these two black lines, they are the maximum value of voltage and current. So when you project it on the y-axis, you get V max sin omega t and I max cos omega t. That means those are the projection. So those are, when you are projecting it on the y-axis, you are getting the instantaneous values. But so those are the instantaneous values. Okay.
Yeah.
Instantaneous voltage, instantaneous current, but those vectors look like this, and you can clearly see there is a phase difference of
Pi by
2 between them. Okay. Okay, so this is so this is overall summary of a inductive circuit. Okay, so always remember that voltage leads the current by an angle pi by 2 in an inductive circuit. Okay, you take a snapshot of this.
Take
This one with this. I will change. So. Okay, I'll drop it.
Yeah.
Okay. So now how much is the power consumed in an inductive circuit? Okay, so the power consumed in an inductive circuit is equal to power P instantaneous. Okay, P instantaneous. If you derive it, you will find it as minus Im into Vm into sine 2 omega t right, divided by 2. So if you multiply it, you can derive it actually. So power is nothing but your voltage into current. So instantaneous voltage and instantaneous current. M stands for max value. So one should not confuse that M. Sometimes max or mean, 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 that will be there. So power is equal to this. Okay. So let us do one simple numerical on this. Now you have remembered what is the formula and all. So let us do a simple numerical on inductive circuit. Okay. So what is given? A pure inductor of 25 millihenry. Okay. So you have a inductor, so its inductance is 25 millihenry. Okay, 25 millihenry. This is my inductance. Okay, E is connected to a source of 220 volt. So this is my AC supply. Okay, this is my inductor. Okay, so its inductance is equal to 25 millihenry, and this voltage source is equal to 220 volt. Okay, so find the inductive reactance RMS current in the circuit at frequency of source is 50 Hz. So you know my household frequency of supply voltage is equal to 50 Hz. Okay.
Yes.
Okay. So this is my power supply 220 volt. My frequency of the power supply is 50 Hz. My inductance is 25 millihenry. Okay. If this is the case, find out the inductive reactance. So inductive reactance is nothing but your XL. Okay. So this XL is nothing but your omega L. Okay. And omega, you know, omega is angular frequency, which is 2 pi by t. Right?
Yes.
This is my omega. So this omega is nothing but your 2 pi f also. 1 by time period is equal to frequency, right?
Yeah.
So there are two things. One is angular frequency and another is frequency. This angular frequency is nothing but your omega, whereas frequency is your capital T. Okay. So what is angular frequency? The angle covered by per unit time.
Radian.
So it's unit in T capital in time period T, it is covering an angle of 2 pi. Okay. So in T it is covering 2 pi. That's why velocity is nothing but your angle covered divided by time. That is angular velocity, right? Right. So theta is 2 pi. In capital T time it is covering 2 pi angle. That's why your omega is 2 pi by T. Right?
Yes.
That is called angular frequency. So you always remember what is frequency and what is angular frequency. Omega is angular frequency. Capital T is the
time period.
Capital T is the time period. So 1 by T is the frequency. So F is like per second, which is hertz. Okay, that is F.
Yes.
Time period unit is second. Okay, angular frequency unit is radian per second. Radian does not have any unit because theta is equal to L by R. Right?
Dimension.
Yeah. So find the inductive reactance and RMS current in the circuit. Okay. So inductive reactance we have to find out. So XL is equal to omega, we know 2 pi F into L. Okay. So this millihenry we have to convert it into Henry so that everything is consistent in unit. Okay. So it is 225 into 10 to the power minus 3 Henry. Okay. Then this is 2 pi 2 pi FL. Okay. 2 pi into frequency I know 50 and then L I know 25 into 10 to the power minus 3. So this unit is ohm. Okay, this inductive reactance unit also is ohm.
Yes.
Yeah, so this becomes kind of 2 pi
100.
into 50 into 25. So this 5 if you cancel, it becomes 100, right? Okay, so if this is the case, it will become 12500 into 2 pi, right? So it will become 25000 into pi. So yeah, so we have made a mistake
It
here.
will be 1 by 100.
So we have made a mistake here. This is 1 by 100. So 10 to the power minus 2, right?
Yeah.
Minus 2. So it will become 125 into 2 pi divided by 100, right? Divided by 100, right? So 250 pi divided by 100. This becomes 2.5 pi, right? So 2.5 pi is nothing but if you multiply it, you will find it at 7.85 ohm. So this is the answer of what is the inductive reactance, okay? So then what is the RMS current, okay? So IRMS is equal to VRMS divided by inductive reactance, XL.
Yeah.
Voltage by in inductive circuit, it is not resistance, it is inductive reactance. See, this coil also has a resistance,
Yeah.
but that resistance is negligible. That is the assumption. Every coil, every wire has a resistance, right?
We avoid
every
that.
coil and every wire will have a resistance, but in this
resistance.
case, they have just ignored that, okay, it is almost zero or whatever. So, that we know IRMS is equal to VRMS by XL. So what is VRMS? This is tricky here. So whatever power supply you are getting at your home, that is nothing but your VRMS.
Understood.
So this VRMS is 220 divided by your inductive reactance, which is 2.55. Okay, so if you divide it by dividing it, so 220 into 2.5 into 3.14. So it will be something around 220 divided by something like 7.85 or whatever. Okay, so then you get it as some 28 ampere. So that is the answer. Okay, my RMS current is 28 ampere. My RMS current is 28 ampere, and my inductive reactance or XL is equal to 2.55. Right? So similarly we will do next the capacitive circuit. In capacitive circuit, that is called capacitive reaction, XC. Okay, which is nothing but 1 by omega C, which is nothing but 1 by 2 pi FC. Okay. Understood. So let us we'll do next one by one. We'll small derivations will cover. So we'll do with the inductance now. Next we'll do capacitance. Next we'll do LRC. Then we'll do one LC circuit, which is a kind of a oscillator kind of thing. LC circuit is nothing but an oscillator. You will get some numericals on LC circuit, oscillator. What is the frequency of this oscillation? You will ask. We had solved one CET question on that. So that we won't get into too much of derivation. We'll just find write down what is the formula. So this formula you have to remember. Except another thing is the phase difference. Okay.
Where it lags and where it leads.
Okay.
Here it will voltage will lag.
Just remember always. If you remember one thing, other thing will be clear. So in inductive circuit, voltage leads by pi by 2. That means in capacitive voltage will lag. So just remember, in inductive voltage leads, in capacitive voltage lags, in resistive anyway they are in phase. Okay. The picture is like this. Okay. So if this is my current, okay. So in inductive circuit, my voltage will be like this. So this is this is voltage. In inductive circuit, it will lag. And if this is the voltage, in capacitive circuit, it will. In inductive circuit, it will lead. In capacitive circuit, it will lag. Okay. So when you will have resistor, force, inductor plus capacitor, then the relative magnitude of these two values will decide how it will be. Like whether if the inductive reactance is more than capacitive reactance, then the resultant will be up. If resultant will be up, the angle will be voltage will lead. If inductive reactance is more than capacitive reactance, then voltage will lead.
Yeah.
But if capacitive reactance is more than inductive reactance, then voltage will lag.
This is an LRC circuit.
In LRC circuit.
Whichever the magnitude matters.
Forget about resistance. If inductive reactance is more than capacitive reactance, voltage will lead. That means if inductance, capacitive, if inductive reactance dominates capacitive reactance, then voltage will lead. If capacitive reactance dominate inductive reactance, then voltage will lag.
Understood.
Okay. So if capacitive reactance, if capacitive reactance dominates inductive reactance, voltage will lag. So if
it will lead.
If inductive reactance dominates, it will lead, voltage will lead. If capacitive reactance dominates, voltage will lag. This is always one thing if you remember, okay, in inductive circuit, voltage leads voltage leads current by 90 degrees. So other things will automatically you can remember, okay? Okay, fine. We will do capacitive and LRC circuit in the next session.